All right, welcome back to the third lecture in the groundwater module of water resources. In this lecture, we're going to take a little bit of a deeper dive into aquifers and how we classify aquifers and the different types of aquifers. We'll revisit a concept that we've talked about quite a bit this semester at different points, including in some of the earlier groundwater lectures. And it's the water table. The water table is the boundary between pore spaces that are unsaturated and saturated. So above the water table, above the water table, the pore spaces are not completely filled with water. They can have some water in them, but there's also going to be some airspace. And it's this above the water table is a zone where we have infiltration and percolation. We usually call the unsaturated portion of the aquifer the vadose, so that would be above the water table, and the saturated portion the phreatic zone, which is below the water table. So a couple of terminology or vocabulary words there that you should familiarize yourself with. And we went over the figure here on the right in an earlier lecture, including talking about the boundary between the water table above and below. What I want you to keep in mind is that the idea of a water table is something that's mostly relevant in this concept and this understanding to an unconfined aquifer. So you'll see here that the subtitle on this slide is Unconfined Aquifer. I am going to define that term in just a few moments, but the idea of a water table is relevant to unconfined aquifers. All right, let's talk about aquifers and confining beds. From the groundwater perspective, there are only two types of rocks. So maybe you took an intro geology class or somewhere had to learn some rocks and minerals. You probably learned a lot of different rocks and minerals like granite, limestone, sandstone, shale, basalt, all these different types in a classification. That's a classification based on their mineralogic composition and some of the broader geologic processes that form the rock. But if we want to classify rocks based only in terms of aquifers, we'd only have two types of rocks. All rocks are either aquifers or confining beds. One thing I'll remind you from a water resources standpoint, the definition of what is an aquifer and what's not an aquifer is one that is subjective to the human experience. So an aquifer is any rock or any sediment that contains water. So any porous earth material that contains water that can be extracted at a rate that's useful to supply human consumption needs. Right? A confining bed would be something that doesn't meet that criteria. A confining bed is a type of rock or sediment, a porous media, that cannot supply water fast enough for human needs. In other words, it's got a low permeability. Right, so aquifers and confining beds. I guess if you took intro geology from me, that rock test would have been a little simpler. All right, unconfined aquifers. Of course, we have two types of aquifers. We've already talked about unconfined aquifers in many of our examples so far in these modules. But first, an unconfined aquifer means there's no confining unit above the aquifer. So water can move freely from the surface of the earth to the water table. There's no shale layers or other impediments in between. Water only fills part of the aquifer. So there is an unsaturated zone above the water table that's not filled with water. The upper surface of the saturated zone is free to rise and decline. So the upper surface of the saturated zone is, of course, the water table. That's the upper boundary of the saturated zone. So in a wet season, when we have a lot of percolation, the water table may rise. In a dry season, when we have little or no percolation, but we have roots removing water from the maybe from the aquifer, if they reach down far enough, or we're just continually draining a portion of that aquifer to supply base flow for the stream, the water table could fall. And if we put a well, if we install a well, the water level in the well reflects the level of the water table. So if we put a well in, the water in that well will rise up to the level of the water table. Confined aquifers are a little bit different beast. A confined aquifer has a confining bed on top of it. Water will completely fill the aquifer. There's a little caveat there, but it completely fills the aquifer. And the water level in the well reflects a potentiometric surface, not a water table. Talk about potentiometric surfaces in a minute, but the water level in a confined aquifer reflects a potentiometric surface. Recharge zones are geographically limited. Remember, when we talked about recharge zones and contaminant pathways in the previous lecture, we were talking about unconfined aquifers, and in unconfined aquifers, essentially the whole watershed is a recharge zone. But recharge zones in unconfined aquifers, or in confined aquifers, are much more limited. Confined aquifers can have both flowing and non-flowing wells. I'll explain that more in a second. And generally, confined aquifers, if they go deep enough into the earth, and sometimes they do, they can have increased temperatures with depth, because the aquifer goes deep enough that the geothermal gradient applies. As we get closer to the center of the earth, temperatures tend to rise. So if we have an aquifer that extends thousands of meters below the Earth's surface, the temperature of the water can be quite high, and if that water can have a pathway that allows it to flow back to the surface at a spring faster than it cools down along the geothermal gradient, you get a hot spring. All right, come back to confined aquifers in just a moment, but before I can fully finish the definition of a confined aquifer, we need to talk a little bit about wells. Okay, so wells are something that humans construct. Normally we would drill a hole from the Earth's surface and penetrate that hole down deep enough into the earth to intersect the water table or the potentiometric surface of the confined aquifer. So let's pay attention here to this well. You can see that we have an aquiclude. An aquiclude is a fancy word for a confining bed, a confining unit. So unconfined aquifer is above any aquicludes and has a direct connection that water can flow through, can percolate through from the surface into the water, to the water table and into the groundwater. Right? So our well, often in a lot of wells these days, they'll drill a hole, maybe a 4 or 5 inch diameter boring, so a hole maybe this big down into the earth, until they hit water. As the drill bit goes down, they'll often also push in a well casing, and a well casing can be as simple as PVC pipe, the same type of pipe that you probably have under your sink that the drain goes into. If you open up the cabinet and look at where the drain in your sink goes, there's a piece of PVC pipe. That pipe's probably 1.5 or 2 inches in diameter, so something like that. Here we're talking about a pipe that's probably 4 inches in diameter. But that is the casing. The casing does two things. One, it keeps water from penetrating into the well boring from parts of the aquifer that you don't want. So it seals the well off from undesirable portions of the aquifer, places where you don't want water to get in, and it keeps the hole from collapsing. You drill that hole down in, if you have a semi-consolidated or unconsolidated aquifer, you're going to put a hole in a pile of sand. The sand's just going to collapse in unless, as you drill that hole down in or drill that sand out, you simultaneously push a casing in. All right, at the bottom of our well, we'll have a well screen. This is pretty much what it sounds like. Holes in the well casing, so holes in the pipe that are covered with some sort of screen that keeps sediment out but lets water in. Sometimes the well casing is a specially designed piece of PVC that has small grooves cut into it that act like a screen. They're just small enough grooves that water can flow into the well, but sediment can't quite get through. Maybe the finest sediments can. All right. Now, that well is completed to a depth within the unconfined aquifer in this case. So the bottom of the well is above a confining unit, and so this is the unconfined aquifer. We can pump water out of that well to use it. If we pump the water fast enough, we'll actually get this cone of depression around the well. This is just where the best analogy I can think of for this is get yourself a milkshake. Who doesn't need a good excuse to go get a milkshake? You need one that's really thick though. Put the straw into the milkshake and suck really hard. And what you'll see is a cone of depression will form around the straw as you remove the ice cream, the milkshake from the bottom of the straw. You get collapse of the ice cream down in, forming a cone or a hole right around the straw. And because the ice cream is viscous, the ice cream at the surface actually has trouble flowing in and filling that cone of depression. If you give it a second, if you suck really hard, create your cone of depression, and then stop, the top of the ice cream will level out and the cone of depression will disappear. Same thing happens in a well. If you pump really hard, you actually pump all the water immediately around the well out faster than new water can flow in, and you'll get a cone of depression. If you stop pumping, things will catch up, and the cone of depression will fill in with water from the surrounding aquifer. In this case, the cone of depression isn't being caused by viscosity like it is in our milkshake model. It's just that because there's only a certain amount of permeability in the rock, if we remove water really fast, the permeability limits how fast water can come in to replace that. And it's easier to get the water out of the areas immediately surrounding the well than it is to get water in from further away. All right, so that's an unconfined aquifer in the well. One thing I'll mention here is I've got a grout seal put in. This is just a seal. Usually it's an expansive clay or something like that, a clay that when it gets wet expands, and they'll put that around to plug the well along the surface to get a tight connection between the well casing and the soil. You put that in to fill any gaps. It's sort of like caulking a crack on your house or something so that water can't get in or out, because we don't want contaminated water from the surface to come along the surface, intersect the well casing, and then flow down the side of the well to the aquifer. That sort of creates a really advantageous macro pore. So we want to seal the casing off from the surface. All right, moving to our confined aquifer. Here we've got an aquiclude. So this aquiclude, think about it like a clay or a shale, something with really low permeability. So water from the surface can come down to the unconfined aquifer, but this water in the unconfined aquifer is isolated and can't penetrate through this aquiclude. So the water under the aquiclude has to be coming from somewhere else in the distance, and I'll explain that geometry that allows that. And for now, just know that the water in the confined aquifer is not hydrologically connected to the water above it. And assume that this well, where it's penetrated the aquiclude, that well is well sealed there so that water can't travel along that penetration between the two aquifers. Now the well screen here is the only place in either well that water can get in. So this well can only draw water from the confined aquifer. But because this confined aquifer is under pressure, so because the water in this confined aquifer is under pressure, when we punch a hole through the aquiclude and provide an easy porosity, the well, that water can flow up, it flows up to some level that's at equilibrium with that overall pressure within the confined aquifer. That's why the level in the potentiometric surface in the confined well, the potentiometric surface in the confined well is higher than the water table in the unconfined. And the best analogy I can think of here is to think about a waterbed. I know waterbeds sort of went out of style 30 years ago, but you probably have an idea of what one is. If you took like a metal tube that was sharp on the end and you punched it into the waterbed, and then you had a friend jump on the water bed on the other side of the bed from where the tube is, which would create a bunch of pressure within the mattress, that would cause water in the tube to squirt out, right? You'd press down on one side of the mattress and you'd create pressure in the mattress itself and the water would shoot out. That's what's happening here, um, more or less. We have the confined aquifer. The water is entering the well and it's under pressure and it rises up to the level where the pressure equalizes with the overall gravity. Now, if the amount of pressure in the well is great enough, the water may actually flow up and shoot out of the surface. If you've ever seen some of the movies or videos where they drill an oil well and get a gusher where the oil just shoots out of the surface, it's because the oil is down in a confined aquifer. In that case, the confined aquifer has a fluid that's a hydrocarbon instead of water, although there's some water in there too. Once they drill down, they've got a well, they're drilling down. Once they penetrate that aquiclude and hit the oil, it just shoots out. And they have to cap that off to keep it in there because it's under so much pressure, and they don't even have to pump it. And if you have a water well that's artesian like this, it's called an artesian well or a flowing well, the water's under so much pressure that you don't even have to pump it out of the well. You just put a cap on there and a valve. When you want water, you turn it on and it just flows under the force of the pressure. All right, so let's go back to our potentiometric surface. Talk about that. The potentiometric surface is the analogy to a water table in a confined aquifer. But in this case, that water table, that potentiometric surface is the level to which water would rise to in the confined aquifer if allowed. If we drill a well, for instance, or if there's a spring. And so here what we see is we've got our confined aquifer. Let's talk about confined aquifers for a second. Here we've got what we would call geologically a monocline. We have a bed, a confining unit here, so an impermeable confining unit, and then we have an aquifer, so something that's got a higher permeability, and they've been warped tectonically into this monocline so that this side of the bedrock units have been bent by tectonic forces up to the surface, and then as we get deeper into the earth, they bend down and flatten out. So right here, this portion of this aquifer, this confined aquifer, is actually unconfined right here. Water can rain on this narrow band of surface where we have permeable bedrock and go straight down to the water table. Once it gets into that rock, though, it's trapped there. It's trapped in this unit because it's got a confining bed to the right and above, and a confining bed to the left and below. And remember, the other word for a confining bed is an aquitard. And then as we get underground, if you come straight down from the surface here, this is isolated, this portion of the aquifer, the confined portion of the aquifer, is isolated from the Earth's surface by the confining bed. So water gets in over here, comes down, and then we put in a well, and that well is going to allow water to shoot out of the aquifer under pressure to approximately the level of the water over here in the unconfined portion. This makes perfect sense, right? Just if you have a hose and you put water in it and you raise this side of the hose so it's higher than this side, water's going to flow out of the lower end of the hose until it's at the same level as the water in the other side of the hose. Think about this aquifer, this confined aquifer is just like that hose. Now you'll notice here though that the potentiometric surface has a gradient to it. It declines to the right here so that it's actually lower. That's because there's friction in the system. If there were no friction in the system, if there were no friction that was using up some of the potential energy of the water as it moves between these sand grains or particles that make up the aquifer, then the potentiometric surface would be precisely level. But because there's some frictional loss as water works its way between the particles in the aquifer, the potentiometric surface actually sort of descends out away from the recharge area. So here where our well, the top of the well is below the potentiometric surface, this would be a free-flowing artesian well. You don't have to pump water out. The water's under enough pressure that the aquifer pushes the water up and out of the well with no help. If we had a well out here on this side, so that the top of the well was actually up here in the land surface, which is above the potentiometric surface, the water in the well would naturally rise to the potentiometric surface, and then you would have to pump it the rest of the way to the surface. So you'd have to pump it from here to the surface. And so that's what a potentiometric surface is. It is the water table. Well, I'll take that back. Let me rephrase it this way. The water table in an unconfined aquifer, this upper unconfined aquifer, it's a potentiometric surface, but it's not under any pressure. So a water table is a special type of potentiometric surface that's not under any pressure and is free to rise or fall. The potentiometric surface is a pressure-driven level that's dependent on the elevation of the recharge area and the water table in that unconfined portion of an overall confined aquifer. Okay, so artesian flow, we talked about this well over here where the land surface is below the potentiometric surface, so any well in this area will naturally have natural pressure-driven flow out of the well with no necessary pumping. This is what's going on here. This is an artesian spring in, I think in the Chickasaw National Refuge, National Recreation Area in Arkansas, and this is an artesian spring in Sulphur, Oklahoma, in that recreation area that's run by the National Park Service. You can see a park ranger right here. If you look closely, you can also see some people who've come with water containers to fill up their containers from the spring. So some people believe there's medicinal value to artesian aquifers or hot springs. Not all artesian aquifers are hot springs, but some are, because they have usually unique mineralogical ingredients in the water that the water gains as it flows through these artesian systems. But this is a free-flowing. This isn't being pumped up by some pump like in a fountain. The potentiometric surface is the top of this. By definition, it's the top of this artesian flow. That's how much pressure the well at this spring is under. There was a natural spring here, but they've put a well in so that it doesn't clog up. Because all the mineralization actually keeps clogging it, and then it finds a new place and shoots out there. So they put a well in so that they could keep it in this spot. But that's the potentiometric surface, right there. That would be analogous to this potentiometric surface. Somewhere up in the Arbuckle Mountains, off in the distance from this well, there's an unconfined portion of this aquifer where recharge is occurring, and that water is flowing deep underground and then has found a pathway to the surface through this well, and it flows out naturally. All right, so now that we have an idea about confined and unconfined aquifers and recharge areas and contamination, we can think about the natural conditions. What kind of aquifer is this? This would be an unconfined aquifer because we have a water table that's got a free connection to the surface. If we put a well in there and pump it hard enough, we will create a cone of depression around that well because that well starts to draw water towards it. Notice that reversed the flow from the stream. And if we pump the well hard enough, create a big enough cone of depression, the gradient of the water table reverses and water starts to move away. We can actually draw water from the river into the well if we pump hard enough in the right aquifer. And that can cause problems or be a solution to other problems. Here's some examples on the right side of our slide here. We have a treatment facility, and that treatment facility is injecting water into the subsurface. So this is an injection well, and in an injection well, we actually pump water down into the aquifer. So we're recharging the aquifer artificially by pumping water in. In this case, we have water that's being treated, maybe from municipal wastewater that's being treated and then pumped back into the aquifer. We have wells over here that are in the floodplain that are pumping hard enough to draw water from the stream to create a hydrologic gradient that pumps water from the stream out of the well. The reason you might want to do this is by forcing the water through this porous media, the sand, you got a great big filter. Sand and the clays in it can actually give you some filtration of the river water and clean it up for free naturally, or for the cost of pumping it out of the well. You probably are still going to have to do some further cleanup before you can pump that to people's houses. And they're showing you here that we have a confining layer, the gray layer here. So we have unconfined wells in the unconfined aquifer and wells in the confined aquifer. And these processes, the injection well is injecting into the confined aquifer. The floodplain well here is withdrawing water from the confined aquifer to get water from the river, because the river is connected to the unconfined aquifer. All right, that wraps up the lectures for the groundwater module, and I hope now you have a better understanding of what groundwater is, what different types of aquifers exist, the relationship of those aquifers to the system, to the surface, either confined or unconfined, some concepts like unsaturated and saturated zone, or vadose zone and phreatic zone, and some of the ways that aquifers can be contaminated, and some of the ways that we can actually use aquifers to store and clean up water, as in that last slide. All right, thank you.